Great. Okay. Hello. Hopefully you had coffee, are awake and ready. Yeah? Okay. So now we're going to start looking at how the knowledge of the Hamiltonian, scattering, and all the prior discussion is going to help us to try to understand how collisions are going to modify the ticking of the clock. That's the idea. So again, we're going to go to the case where we're focusing on a single lattice site, a single pancake. In a single pancake, in a 2D, you can imagine the potential as a 2D harmonic oscillator. We are going to have at the moment thermal fermions, and they are cold but not quantum degenerate. So we're going to have a thermal cloud that is populating the different harmonic oscillator levels, yes? And what we are going to understand is how collisions, the fact that these atoms are colliding with each other, is going to modify the dynamics. So first, notice that because we have a deep 1D lattice, the trapping frequency that says the spacing between the levels is of the order of a few or 100 hertz or 500 hertz is large compared to the collisions that, as I mentioned before, they're super weak because they are suppressed by the centrifugal barrier, and we're going to have an interaction energy that is of the of hertz. So we're going to be good to do perturbation theory. Now, because of that, so what happens is that if I am going to populate the harmonic oscillator levels of the atoms, I prepare them in the harmonic oscillators. The point is that if, of course, collisions, the collisional Hamiltonian is not an eigenstate of the harmonic oscillator levels, so there is going to induce dynamics, but because the energy of the collisions is so weak compared to the energy of changing levels, that is of the orders of few 100 hertz, then these processes are not going to happen. They are going to be suppressed. And therefore, to leading order, the only thing that we are going to care is terms that flip the spins of the atoms, but frozen the dynamics of the motion. So basically, what I'm going to have is that my atoms are going to be in these harmonic oscillator levels. And you can imagine these harmonic oscillator levels as a 2D synthetic lattice. The lattice is in energy space. It's not a real lattice. It's a synthetic lattice where the atoms are going to be frozen. And the only thing that they can do in this lattice site, energy lattice site, is to change the spin. So this is an approximation, this assumption of no, what we call no mode changing collisions, but it's going to tremendously simplify the modeling of the problem. So now, in the slide before, when I showed you this bad, here, these very complicated matrix elements, here, these are going to be the complex matrix elements of the interactions. Something that you are going to realize is that these are based on Hermite polynomials, and the Hermite polynomials are very delocalized in position space, yes? So because they're very delocalized in position space, that means in this energy lattice, the collisions are going to be kind of all-to-all. In some sense, if you have a particle that is, let's go to the case of momentum versus position, that is very similar. If you have a particle that is very localized in position, it's going to be very delocalized in momentum, and the other way around. If there is very delocalized in momentum, it's very localized in position. So if even though the particles only bump into each other when they're in the same location, this is the contact interaction, the pseudo-potential approximation, if their wave function is very delocalized, then they can talk with any other particle because they're all delocalized, yes? So basically, so what happens is that if you look at the interaction between the different energy levels, are going to be very long range, and I'm going to explain a little bit more like that. But let's try to look at we have this Hamiltonian that have, I'm sorry, I have to go back and forth many times. So this Hamiltonian has, you destroy a particle in harmonic oscillator N3 prime, and destroy a particle in M3 prime and N2 prime collide and create a particle in M prime and N. That's this matrix element. But as we said, not all the matrix elements participate because only the ones that preserve the motion are going to enter. So basically, we're going to have a delta function, and among the terms that we are going to allow are two different types. You destroy a particle in N and destroy a particle n prime, and you keep the same n prime, and the alpha and beta are not exchanged. So you are going to have something that is alpha, C daga alpha, C daga alpha, C alpha. I'm moving this. Remember that you can always move two operators because they're fermionic and without changing the sign. So you are going to have a term that is C daga alpha, C alpha, C beta daga, C beta. So this counts the number of particles in mode n particle type alpha, and same for this other term. And you can think about that this term is going to be related to as a SC term, because SC operator, so let's see if I can, you can see here, so SC operator is going to be associated, I mean the C operator is going to be the number of particles in up, so minus the number of particles in down. I can have an n. Yes, so you can see that this term here is diagonal, so because it's half alpha alpha, so this term is going to be C daga n, C n minus C daga n, C daga n. Yes, same n, same spin here, same nuclear spin, yes. And you know also the particle is conserved, so n up, n plus n down, n is equal to 1. So any operator that has in this form, I'm going to write it in terms of SC operators. So the first term here that enters in the Hamiltonian, I have SC. I have other type of term. You can see for the particles, I mean, always you have to conserve the total number of particles in each mode, but you have a term when you have a particle in mode n prime alpha, and then you are going to go to where is there is a typo here? No, it's good. N C alpha n prime, C daga beta n prime. So this is flipping the spins, yes? And this is going to be a term that has the form S plus S minus n n prime. So what we are going to do, all this exercise is going to be how we are going to write this complicated Hamiltonian that I wrote before in terms of a simple spin model that I can understand. This is the idea. So let's try to understand this. Now, respect to the range of the coupling constants, I gave you a very complicated formula in terms of integrals to compute the strength of the matrix elements that couple the different harmonic oscillator modes. So remember this beast. But remember going back to the pseudo-potential approximation that we were saying for P-wave interactions, the Hamiltonian, the coupling Hamiltonian in momentum space for states that have the same K was just proportional to K squared. It's proportional to the kinetic energy of the particles, remember? It's proportional. This was, remember, if you look back at the formula that I wrote, the P-wave matrix element was a scattering volume time a term that depends on K squared in this case. So if you are going to try to translate this to the harmonic oscillator, we're going to say, well, K squared, because of the equipartition, is going to be proportional to the temperature of the particle. Now, B cube, of course, remain B cube, and the volume is going to be the area of my wave functions times the harmonic oscillator length along the C direction, because this remains quantized along the C direction. But now, if you remember, if you have a thermal gas, the width of the thermal gas is proportional to the square root of the temperature. Yes, the hotter, the wider distribution. So something very nice is that for these B-wave interactions, because the area is proportional to the width square and therefore linear with the temperature, this term cancels, and we have collisional matrix elements that are independent of the temperature. This is a blessing, because then we don't care what temperature, that are very, very universal. So if I now look at these matrix elements, I do the algebra. First, they are very, you can see that they're very narrow, and therefore more or less all of them are the same. But the important part are the width of these matrix elements and the interactions. I mean, the mean, big wave, and the standard deviation are really constant in temperature. So we can ignore temperature, And also, well, the rabbit frequency can also depend on the harmonic oscillator states that we want. So typically, if you are going to have the rabbit frequency, actually is going to be, the rabbit frequency is going to be at the rabbit frequency, and then you are going to have the integral of e to the k dot r, and then you are going to have the harmonic oscillator wave function. This is the transition matrix element that a laser can introduce between different harmonic oscillator states, because we are occupying different harmonic states. This, of course, is not necessarily zero. This term is proportional to a Laguerre polynomial that is depending on the what is called lambda key parameter. If the lambda key parameter is associated with the wavelength of the laser times the harmonic oscillator length. So, the fact that we have particles at finite temperature, we are driving there with the laser, can introduce some type of transition between the harmonic oscillator levels. The advantage here is that this K is along the C direction. Yes, so this is going to be KCC. And therefore, if we are talking about a matrix element, for example, I mean, this was a vector. If we are talking about matrix elements that are along the X and Y direction, this goes out, this term goes out, and because the wave functions are orthogonal, then we don't have inhomogeneities from the laser frequency. So that's good. So that's why we don't have inhomogeneities from the laser frequencies. We don't have, and then it's independent of the temperature. So this allowed me to write a very pristine model. So, okay, I was thinking that I was going to stop in the good in the prior one. So, but now we went, so this is what we done. So now, when we write the Hamiltonian, this complicated Hamiltonian into spin operators, this is the model that I'm going to write. So, and this is an exercise that this is in specifically an exercise that I want to work out during the tutorial. But I encourage you, please take a picture of this, and I want you to try to work this formula out from a very simple case. So what we know what I want you to do that is only for two particles. We only need to consider to derive this formula, we are going to consider collisions between the two particles. So we are going to have a particle in harmonic oscillator. I have one particle in harmonic oscillator N1 and a particle in harmonic oscillator N2. They're going to be frozen. That's it. And as I wrote before, these matrix elements, so there are possible states. There are the triplet state, the triplet plus, the triplet minus, the triplet 0. And these are going to be, has by definition a symmetric wave function. All of them, I mean, any of them is going to have a symmetric wave function. And they're going to interact with P wave. The singlets is going to have an antisymmetric wave function and is going to interact with the S wave. And the matrix element in this type of this interaction is going to be triplet. This is for example, let me call it GG, EE. This is interact EG plus GE, and this is EG minus GE. So this is going to be a matrix that are going to have BGG, BE, BG, and then you're going to have EG minus. This matrix can be rewritten in terms of spin operators and has this form. When you rewrite this matrix in terms of spin operators, has this form. So this is the exercise that I want you to do. So it has a term that is S dot S, and this S dot S is proportional to the difference in scattering lengths between the P wave and the S wave EG. It has a Ising term. This is Ising, sigma C, and is proportional to the BE plus BGG minus twice BEG. It has a constant, a term that is linear in SC, that is the difference between these two terms. This is proportional to Z. and I have an identity. So it's this Hamiltonian that we're going to write, and this is what we are going to use to solve for the dynamics of the spins. And the advantage now is because these modes are delocalized. Here there is a dependence on the mode. To a simple approximation, I can take this, well, first, if I start with an initially polarized state, it's an eigenstate of S dot S. It's an eigenstate, it's fully polarized, an eigenstate, and therefore I'm not going to change it. So I can ignore this term. And the Hamiltonian reduces as an Ising model, and with coupling constant chi and c, from before chi and c, these terms. And because, as I showed, that the coupling constants are independent of the temperature, very, very pristine, to an excellent approximation, I will pull this out of the sum, and I just write a Hamiltonian in terms of collective spin operators. Yes, so I'm going to, instead of caring what individual atom is doing, and because the coupling constants are going to go out, these sums are over all n's and all nj's, so I'm going to have a collective spin operators that sum over nj equal to 1 to nj, his j equal to n. These are collective spin operators. And I'm going to write this Hamiltonian in terms of these mean coupling constants that depends on the scattering volumes and this collective mode. So from these all four Hamiltonians that I wrote in the first slide, we reduce the dynamics to something extremely simple. This Hamiltonian is the one that I'm going to use to determine how interactions, collisions, are going to modify the ticking of the clock. And from these Hamiltonians, I'm going to start to do even a further approximation that we call mean field approximation. So in a mean field approximation, I don't care what is each atom doing, but how an atom is affected by the presence of other atoms in the array. That's the definition of the mean field. So I look at a given atom, and the others are just an effective field that modify the behavior of my atom. And so that's the idea. I don't care about the specific any of the other atoms are doing, I just care about the average. So what matters is that this Hamiltonian, that is still simple, but I can still simplify even more. I can rewrite it as I factorize this term. Instead of SC squared, I'm going to have twice, because I have, it's like factorizing SC times SC, and so when you do a mean field approximation, if you have a Hamiltonian that is a B operator, the mean field approximation is going to be expectation values of A, B, plus A, expectation value of B, minus A dagger, B dagger, the expectation. This is a constant that is not important. And then, because I have the same operator as C squared, this is the factor of 2 that I get. Okay, so this term, then what I get is that the shift in the ticking of the clock, remember that the tuning is what I wanted to determine to lock the laser with the atomic transition. Now the tuning is changed by or the terms that accompany the C operators are always going to be modified by these other operators that depends on the scattering volumes. A constant term that, of course, depends on the number of particles, and a term that depends on the average SC. So what it's telling me is that the shift depends on the first tipping angle of the Ramsey sequence that sets this pulse area, remember, of the state. So interestingly and very nicely, the clock measured what is the change in the ticking rate as a function of the excitation fraction. And indeed, they saw the linear dependence that this very simple model predicts. So with this simple theory, we were not able to predict not only or tell the clock that they have to operate at this point where the ticking, changing the ticking rate because of collision is 0, here it cancels, but also these scattering volumes are really hard to compute in theory, but we can fit this line and get an expression for why is the chi and c bar, and actually start to get some insight on these scattering volumes. So yes, so basically we were operating at this point with this density shift is 0, and then we were able to actually control a lot, and the clock became, please speak out loud. Uh-huh. Even more before? Mm-hmm.
Is that the Hamiltonian for spin squeezing to generate spin
Yes,
squeezing?
I'm going to go, yes, exactly.
Because you are applying mean field, then you don't have spin squeezing anymore, right?
Yes, wait,
Okay.
wait one slide, wait one slide, yes. Please.
So I see you are interested in the SU2 symmetry, but can you rotate one of these terms to implement like an LMG model? Like,
In order to have these terms, we will have to add a transverse drive to implement an LMG model, yes, because SSC squared by omega Sx. And
yeah, these two terms, they commute, no, right? So these three terms, actually, they commute with each other.
exactly. So we can add a drive, and we did it. We call it Rabi spectroscopy. I'm not going to talk about it, but we did see a transition, the LMG transition there. Yes.
Yeah, thank you.
So going back, this is the expectation value. We use a mean field theory, but it was useful because it tells us where operate at this point where there was no density shift on the clock, and the clock became, at that time, 2014, the best clock in the world because it was not, well, many other things, but in particular, it was not sensitive to collisions. But okay, so at this point, that is great. Now, however, let's look at, when you look at the expectation value of the collective spin, that is what we care. So the coherence, how large is the collective spin because of the dynamics in the presence of the density shift, or delta only is going, remember, is going to rotate in the XY plane. That's the dynamics. But the question is, what happens when I have not only one atom, we have many atoms, and the Hamiltonian is not just delta SC, but we have these more terms in the dynamics, yes? So at the mean field, this is the pictorial representation of the clock. You have a 1D lattice, many pancakes, and we have a Poissonian distribution of atoms in each pancake. They are not talking to each other. At the moment, we are ignoring tunneling. And the question is, what happens when I model these atoms with the model that I just told you about? So each one, the atoms are in a pancake. And the important part, as you can see from the mean field picture, is that there are terms, for example, NSC, remember? And that means that the pancakes that we have with larger number of atoms are going to tick faster compared to the pancakes that have a smaller number of atoms. And in fact, you have, I'm trying to do a cartoon here, but the fact that we have some cloud processing, some part of the cloud processing at different rate of other cloud, this is going to introduce dephasing. Because now, if I start with all atoms, some tick faster, some is slower. When I try to look at the collective spin, that is the sum over all spins of each atom, is going to decay. And exactly this is what they were seeing in the clock. But it was very interesting. So I was trying to do a mean field approximation. This was the experimental data. And these are different tipping angles. So you are going to have from 2 pi over 9, the closer to the equator. And then you are going to have different tipping angles. They were doing Ramsey spectroscopy. And this is what the clock was observing. And these were my mean field calculations based on the Hamiltonian that I show you. I also was including some type of losses. Unfortunately, atoms in the excited state, they decay. So I had a little bit losses in the model. That's why sometimes it looks a little bit weird here. But anyway, you can see that only this line was consistent with what they were seeing in the clock. The others were not. And this is the different tipping angles of here. So what if I was looking at what happens with the density shift, what we were seeing is that the points that have higher density shift, this one, were green, whereas the points where the density shift was 0, this is the point where we were canceling, you were seeing that the agreement was very bad. So what is going on? Well, The point is that this mean field approximation that we were using to describe the density shift is not necessarily good enough to describe the contrast of the clock, the contrast decay. And the point is that the points where the density shift was higher, then the dephasing was really generated by this different ticking of the clock, of the different atoms in the clock at the mean field level. But if you are going to this point, because the particles are not ticking at different rates because the only term is delta, so there should be no decay. This extra decay was because of the losses. So then why the experiment has seen so fast decay at this point? It was very weird. Well, what we discovered is that there was already seen failure of mean field dynamics. And the question at that time, long time ago, 2013, is how we're going to include of beyond mean field corrections. So the idea was very simple. And the idea was trying to understand the noise introduced by quantum fluctuations. And this led us to develop one of the approximations that I think have been used more often now for dealing with the spin model, that is the truncated Wigner approximation. And I'm going to explain it very simple. So if I have a large spin pointing along the x direction, for example, expectation value of Sx is equal to n half, yes? But clearly at mean field level, expectation of Sy and Sc is equal to 0. But when you compute the variance, if I have a coherent state, the variance is not 0 because Sx and Sy and Sc, they don't commute. So when you have a coherent state, if you look at the variance of Sx is 0, but the variance of Sy/Sc is proportional to, or the standard deviation is proportional to a square root of n divided by 4. So that means that I can recover the quantum noise if I imagine that in my initial condition, my spin is not pointing only along the x direction, but I'm going to assume that my initial state is going to sample this noise distribution. So instead of replacing Sy by 0, I'm going to replace Sy by a Gaussian distribution because it's a noise, it's quantum. So I'm going to do this as a distribution, let's call this A equal tilde square, with a variance that is a square root of n. So I'm going to solve my mean field equations, but instead of starting my initial state along Sx equal to 0, I'm going to assume that Sx have a random value. I mean, I have to put, it's of course when this Sx, or I can normalize it divided by n, is going to have a random value that reproduces this initial noise distribution. So I have to have an initial distribution such that this is going to be n quarter. That's what I need to do. And then I'm going to solve my mean field solutions. So basically, if you are going to do what we did for, if you have a Hamiltonian, a simple Hamiltonian, that is chi C squared, for example, I'm looking at this term. At the mean field level, remember that this Hamiltonian, the mean field Hamiltonian, is 2 chi expectation value of Sc. Yes? So this is an effective magnetic field. I call it this BC. If I have a particle in a magnetic field, and if you look at what is the expectation of S minus as a function of time, what you get is that the expectation value of S minus is S minus at time equal to 0, e to the minus I B C times t. That's the dynamics, yes? So before, what I was saying is, okay, now if I am at the equator, I was saying expectation value C is equal to 0, yes? Because I'm pointing, when I am at the equator in the Ramsey fringe, S equal to 0, Sy equal to 0, and Sx is different from 0. That's it. Now, however, what happens is that this is not going to be correct. So I'm going to replace this BC by, as I said, 2 chi expectation value of SC, but this is going to be a random variable. So the expectation value, when I'm going to compute what is the expectation of Sy, or S minus, is going to be the integral of e to the minus 2 chi SC, let's put it SC tilde, times t, and then I'm going to put my variance here, here. This is y and also SC. For the y, it integrates out because there is no five variable, but I'm going to have minus SC. This is from the initial conditions, yes. I'm going to, with the initial condition, SC is tilde divided by M4. And when you do this integral, and this is integral over SC, because I'm sampling over all these initial conditions, then when I look at what is the value of SC, and SC minus at 0, this SC minus, you are going to have, for this particular case, you are going to have something that is n half e to the minus k squared t squared. Well, maybe a factor of, well, with some prefactors, maybe a factor of 2 here. But the important part is that you can see that in contrast to the mean field, you are going to see that this expectation value of S minus is decaying. Okay, okay, sorry. It's hard to see, okay. So this is the, I'm doing mistake even here. This is the evolution from the mean field solution, and I'm going to do this multiplying by the Gaussian distribution, and I'm sampling all the different initial conditions of the noise. That's all what I'm doing. And then I'm going to have, you can see by including the noise, I can see a decay even just at very simple mean field level. So this is what we see here. When I introduce the truncated Wigner, now we agree very well with the experiment, and we are going to reproduce what they were actually, quantum noise was even influencing the noise of the clock, the behavior of the clock at that time. So yeah, so basically, is there any questions about that? Was it clear? Yes? Yes, please, if not, let me know. Okay, so we consider the spin polarized case. Okay.
So I wanted to ask if the mean field failure for the equilibrium problem or just to the non-equilibrium, which is the runs in decay.
We are always considering dynamics in the clock.
Okay.
There is no equilibrium. There is, it's transient. We are doing Ramsey spectroscopy. That means we start an atom that is in a non-eigenstate of the system is going to evolve, and we are going to see how much phase it accumulates in order to translate the phase accumulated into a population and set what is the tuning of the clock. That's all the game here at the moment.
Okay, thank you.
Okay, so at the moment, so we start with the simplest problem that I deal with the optical part. Now I wanted to start combining this with the spin, and then I'm going to go to the charge, yes? So, or the spin orbit coupling. So let's try to do this spin and orbital, and then let's do a little bit, very little of SUN magnetism, very little. It's going to be just really a small thing. So now we reintroduce the M in the spin operators, in the field operators, because now we're going to have M levels, 10 levels in the ground and 10 levels in the excited state. So now we're going to have different contributions to the Hamiltonian. So now there are going to be interactions between atoms in the ground state. And because you can have different nuclear spins, then we are going to have S-wave interactions. And these S-wave interactions are going to characterize by a scattering length AGG. This is the standard when Subir was writing the Hobart model. Then you are going to have something that is the number of particles in a spin up times the number of particles in a spin down, yes, and up and down. That's what he was writing, very similar here. Now, same for the excited state. You are going to have now a different scattering length, AGG, number of atoms in the excited state M times number of atoms excited in excited state M prime. Now we are going to have two additional terms. The typical notation in condensed matter is the exchange and direct terms. So these terms are, the origin of these terms is super simple, is the fact that the eigenstates of the system are going to be triplet in, so as I was writing before, and this formula is appearing all the time, the eigenstates are going to be this. Now, for example, if I have a singlet in the nuclear spins, or this times a triplet in the nuclear spin, but never just, so if you are going to, maybe, I'm going to write this here. So, for example, if you have 7/2 and 7/2 and 9/2, the eigenstates are not going to be just an state that I have something here and some here. It's not going to be this state. The eigenstates are going to be a superposition of this state and this state. Yes, because they are singlet and triplets, the eigenstates. So that's why when you write the Hamiltonian, you are going to have a term that we call direct, that is in the form that it counts the number of particles in the M state in G times the number of particles in the excited state in M prime. So this is also a diagonal term. So it's the number of particles. You can see M prime is diagonal. But then there is called this exchange term that destroy a particle in M prime in G, destroy a particle in E in M, and creates a particle in E in M prime, is switching the spin, and the G in M. So what happens with these terms is that if I have a particle, for example, here I have a particle in 9/2 in E, and a particle in 7/2 in G, this term is doing these flips. This exchange process is at the heart of many of the Hamiltonians that we are going to write for alkaline atoms with nuclear spin states. So more details of this type of Hamiltonian is going to, you can find it in this review. And the beauty, as you can see, is that I'm not doing anything associated with the nuclear spin here because of the SUN symmetry. Everything here is independent of the nuclear spin state. That makes the Hamiltonian much more simple. So now I'm going to tell you a story about how we probe SUN symmetry in the clock. So the clock, now what we are going to do is that we are going to allow the atoms to have colors. So before, I was only interrogating a spin polarized atom. Now we are going to load the clock, allowing the population of different spectators. That's what we're going to do. The experiment is that now there are many, many colors of the clock. And still, what I'm going to do is that I'm going to do Ramsey spectroscopy, where I have a laser that is resonant only on this transition. Something that is super beautiful of these clocks is that actually they show, and again, if you look at the Martin Boyd thesis that I was mentioning at the beginning for the nuclear spins, actually the clock is able to resolve transition between these two, these two, these two, these two, these two. So they can make sure that they only excite, for example, the 7/2 to the 7/2 in the excited state. How do you think that this is possible? How I can apply a laser, and I'm going to make sure that my laser only transfer atoms from 7/2, or only transfer atoms from -1/2 to here. You need to resolve them, yes? You need to have an energy penalty. So if you look at this picture, you can see that I'm writing that depending on the nuclear spin, you have different energies. That's what I'm writing here. So here is smaller, this is larger, 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 larger. This is a reality, and this comes from the fact that even though the coupling is very weak, there is a different G factor of the atoms in the ground state and in the excited state. So in the presence of a magnetic field, you can imagine that the atoms in the ground state, the tilt, the energy shift that they get in a magnetic field is some, but the energy shift of the atoms in the excited state is much larger. So that means that if I have a laser that is resonant with this transition, it's not going to be resonant with this other or with this other and this is other. So the clock showed the possibility to resolve all these possible levels. That is beautiful. So the clock can even also look at use the polarization, and then, for example, for sigma polarized, can transfer 3/2 to 1/2 and not other thing. So it's able to resolve all these possible states, opening a path for really SUN spectroscopy in this system. So that's how, I mean, it's hidden in this slide, but this is the level of control that the clock has on this. And the difference in G factor between the ground and excited states is approximately 100 hertz per Gauss. So it's weak, but it's significantly for the scales that we are talking about the clock. All right, so what was the experiment? And I'm just going to give you an idea. So the idea is that they said, okay, let's load the clock with all different nuclear spin states. And what we are going to count is the fact that if I interrogate this transition, the 9/2, for example, these other atoms are going to be just spectators. They're not going to be driven because they're of resonance. But nevertheless, this atom can collide with these other atoms in a non-trivial way. The important part is that, well, we already understood the collisions between the atoms in the same nuclear spin. Remember, we derived this ticking rate because of the P-wave interactions. P-wave interactions can happen between atoms in these nuclear spin states, fixed nuclear spin state. But there is going to be S-wave interactions or S-wave collisions between this and this one and this and this one. So these are the S-wave collisions. The important part, and therefore, is going to introduce a density shift. But the important part is because of the SUN symmetry, I don't care if these atoms are distributed this way or this way. I don't care how many atoms are populating all the different nuclear spin states because they're SUN. So I just care about the total number of spectator atoms because this atom is going to collide equally with this one or this one or this one or this one. It doesn't matter. The only part is that there are, if I fix the number of spectator atoms, then that's what tells the modification of the collisions. So it's going to be something that is proportional to complicated, I don't want to enter in details, on the scattering S-wave and P-wave scattering lengths, but the important part is that is the number of spectator atoms what matters. If we see that, then we're going to confirm the SUN symmetry in the clock. And this is exactly what they did. So they do Ramsey spectroscopy in the presence of my spectator atoms. And this is the ticking clock, the change in the ticking rate of the clock versus excitation fraction, same that we did before, but now with different conditions. So in one case, we have all the atoms in the 9/2 state. This is the line here. And then the clock changed the initial population and have only 29% of the atoms in this, and then other atoms in other states. And we can also, now we can interrogate this atom. Remember, it doesn't matter what atom I interrogate because I mean, as long as we do things equally. So I'm going to interrogate this atom and it's going to interact with different clouds, different partners, but the collisions are going to be identical. And if I'm going to go to just a smaller number of interrogated atoms, and then the collisions, of course, is going to be different because it's different n. So we did see that the collisions only depend on the number of spectator atoms as expected, and we were able to determine, and the slope of the lines were identical, independent of it was just set by the P-wave, independent of which nuclear spin I populated. And therefore, we were able to confirm the P-wave symmetry of the SUN symmetry of the collisions at the 3% level. So we think that this is small. I mean, it could be better, but at this level, that's what we were able to measure. So a lot of calculations involve these computations. I'm not showing them to you, but the nice part is that with these calculations and comparisons with the clock, we were able to finally pin down the value of all the scattering lengths and scattering volumes that I grow at the beginning of my table. So they cannot be calculated by theory. I mean, it's very complicated. The atomic structure of strontium-87 is a mess. But we were able to put numbers by comparisons and by using some type of connection. This is with the help of Paul Julien, some connection between S-wave and P-wave interactions. I mean, this formula you can ignore, but I think that what I wanted to point out is that now we have a very precise determination of all the different scattering values and scattering volumes of the strontium-87, and therefore we are ready to do different type of many-body theory, including SUN physics. So this was a note that when we wrote this paper, then we got a call from the person that tracks the publicity in JILA, and she said that she saw this ad about, I mean, I don't know if you know, Big Bang Theory is a comedy, and Sheldon is a very interesting character. And according to the ad, Sheldon was going to come to JILA, and he was going to explain us the spin symmetry, to explain me and June the spin symmetry, SUN symmetry of the collisions. So it was going to be a Big Bang Theory show filmed at JILA, and then it didn't happen, although this was advertised. so fun.
Now, let me understand, because so there was the concrete risk that you and June would have appeared in an episode of Big Bang Theory.
Yes.
This was in which year?
2010. No, this could not be. No, sorry, 2013. 14. This paper, yeah, for 2014.
Would you and June would have accepted?
Yes, why not? Yes, it was fun. I mean, I think June knows the person who writes the scripts. So that he's in Caltech. June did his postdoc with Jeff Kimball at Caltech. So that's why it was the connection. But they didn't came, so we were okay. Okay, so I told you, I mean, you can see it's a very brief description. We could go much more detailed, but I gave you a brief description of orbital spin. But I want now to enter in the other very exciting part, that is the charge degree of freedom. How is that we are going to make these atoms that are neutral behave as charge? And this is through what we call a spin-orbit coupling that naturally happens in the clock. And the only thing that we have to do is to allow the atoms that were frozen in each lattice site, allow them to tunnel. So let me try to explain a little bit and also motivate. So if you are a condensed matter physicist, then a spin-orbit coupling is very important, because in the crystal, there is a coupling between the spin and the orbital degrees of freedom of the electrons, and therefore, when people model spintronic devices or their model topological insulators, then spin-orbit coupling is at the heart of their theory. So there has been a boom of topological insulators. All the physics is really the coupling between the electron motion and its spin. In Microsoft, if you hear about what is happening, I mean, we have to be very careful, but the idea is very exciting. So they said that if you have a superconductor in the proximity of an spin-orbit coupled material, actually there is the possibility to form what is called Majorana particles, and Majorana particles are known to be topologically robust and in principle ideal for topological quantum computing. So there is still elusive all this physics. I think it's a lot of complications, but I think it's interesting to explore spin-orbit coupling for quantum simulation. So in colatoms, spin-orbit coupling has played a big role. Back in before 2016, there has been a lot of progress in rubidium, potassium, lithium. Then there was process even in dysprosium and terbium. But only when we start dealing with alkaline atoms, we're starting to see a little bit of opportunities, because the problem is that you can see a spin orbit coupling, but at the single particle level. And if you wanted to push it in the presence of interactions, because you are talking about atoms that are coupled, very coupled to states that decay very quickly, then the system heats very rapidly. So heating has been, from Raman transitions, has been a very bad issue, trying to see or push more spin orbit coupling proposals in alkali atoms. But the story changes a lot, where we are going to deal with alkaline earth atoms, where we are going to have very nice opportunities. Well, I have to say that perhaps the exception has been Leticia Tarruffel, that she has done beautiful experiments in potassium. So maybe this is, but very is lately. So at the beginning, it was a lot of heating in these experiments. Let's think about optical lattice clocks, and let's try to see why it's so natural. So as I mentioned before, we have a transition that is optical. Means that optical is the wavelength of the transition is small, or the wave number is large. I'm sorry. Okay, I'm sorry. I should have not drinking water. Okay, so we have our laser that has, of course, a profile e to the AKX as a plane wave is propagating. Now this K is large, and this means that the K times A is going to be A being the lattice spacing that is associated with the lattice that has to be fixed, because it's the magic wave lattice that is identical for the ground and the excited state. This Ka is of order 7 pi divided by 6. That means that the phase of the laser changes by more than pi from one lattice side to the next. So what that means, that if I have a clock and I start with all atoms in the ground, and I do a pi half pulse, if these atoms in this lattice side go to the equator, the atoms in the next lattice side are going to be offset by a phase phi respect to the x direction, and the other by a phase 2 phi. So there is going to be different phases, the atoms are going to become distinguishable. And if they don't tunnel, who cares? But when the atoms start to tunnel from one lattice side, they are going to see that my atom, my nearby, has a different phase, and this is going to be very important. It's going to be visible. It's going to be something that the atoms care. So in order to see a spin orbit coupling, the only thing that we need to do is to reduce the lattice depth to be very deep, to be shallow, and allow the atoms to tunnel. Okay, so this is one way that we are going to see this spin orbit coupling. There is another way to interpret what is the physics behind. That is the idea of a synthetic ladder. So you have the atoms. They can be tunneling. This is along the direction of the lattice, and there is the tunneling. But we have two internal states, the ground and the excited state. And you can see the ground and excited states as the legs of a ladder. Why is that? Well, because these two states are going to be coupled by the laser. Now, if I have an atom in lattice site N1, I go from the ground to the excited state because I'm going to absorb a photon from the laser. But at this lattice site, the laser has a phase phi. Now my particle is going to tunnel from lattice site 1 to 0. This is the excited state. I don't accumulate any phase. And then in the other step, I'm going to emit a photon to the laser at lattice site N0 from excited to ground. But in this case, the phase at this site is different than this phase at this other site. And therefore, if I tunnel back and I do a closed loop, then across this placket, there is a net phase phi that is associated with the phase that a charged electron would get if there is a magnetic field in the plane. So you can see that basically the effect of the spin orbit coupling, the effect of the different phase imparted by the laser, is going to emulate as the particles feel an effective magnetic field that introduces a flux phi, like the Bohm-Haranov phase, across the placket. So that's why we say that we are emulating as the particles were charged. This is one way to do it. Now, the other way to understand the spin orbit coupling that is going to be more relevant for the clock, but always depends on how you define time reversal symmetry, because the Hamiltonians that we are going to, I think, I mean, if you are saying the type of spin orbit coupling of the is not of the Rashba type, or yes, but I think it is. I mean, I think you can show that all the properties that you get from this Hamiltonian emulate exactly the properties that you have. I mean, Beren Paredes has a very nice paper showing that, and showing that you can get all the similar properties that you have of topological insulators in this system. So I think it's a matter of how we are going to think about the time reversal symmetry. So if you, well, it's synthetic, be careful, it's synthetic magnetic field. So that's what people call synthetic gauge field, yes? This is going to, it's not, I mean, you are saying it's a magnetic field, it's a synthetic magnetic field. And this is going to be kind of as an effective vector potential that the particles feel. But the properties of the vector potential are going to be depending of the momentum of the particles. It's going to be really more, it's not an static magnetic field. So, I mean, maybe in the next slide, you can see what is more spin orbit coupling. But in the papers, if you add other ingredients, not in this way, but if you add other ingredients, because this is a vector potential, maybe I would say not as a synthetic vector potential that could be connected if it were spatially dependent to a magnetic field, yes? The curve is a magnetic field. And experiments in Ian Spielman were able to add a core in this and measure the magnetic field. But in this case, you can see more like a vector potential, and is emulating the behavior kind of the Bohr and Haranov phase that an electron is going to experience in the presence of a magnetic field. So the terminology is loose, and then there is a very intricate difference between the synthetic gauge fields and spin orbit coupling. I mean, in the paper by Ian Spielman is very well carefully determined and things. But I think it's still instructive to see that you can emulate the behavior of a charged particle in the sense that there is a Bohr and a Haranov phase. Yes, that's clear? So now I think the most useful way to see that is in terms of an spin orbit coupling. And this can be understood now by looking at particles that are moving in a lattice. If you have particle in a lattice, you are going to have an energy that depends on the momentum. And if you are in the lowest band, it's going to be a cosinusoidal dispersion. Yes? So this is going to be, and then tunneling, that is the rate at which you move quantum mechanically from one lattice side to the other, is the same, identical for the ground and excited state. So you have, because we have a magic lattice, you are going to have exactly the same dispersion. Yes? So what happens when I illuminate the atoms that can now move along the lattice with the laser? So what happens if, well, there is a offset, global offset, because there is a detuning. So it's equal for all momentum. Now, what happens is that I have a atom in the ground state, and then I'm going to absorb a photon and I'm going to go to the excited state. As I said, because the photon is an optical photon, I'm going to have a momentum kick. So my momentum, instead of being Q naught, when I transfer to the excited state, I have going to have a momentum Q naught plus the laser momentum. So I'm going to have a kick. Now, this change in a spin linked to a change in momentum is kind of a way to understand a spin orbit coupling. And a simpler way to actually model this problem is to do a gauge transformation. That is basically, I'm going to relabel the momentum for the atoms in the excited state, relabel the momentum without changing the physics, and I'm going to move the momentum. So still, I'm going to couple atom in the ground state with an atom in the excited state that have the energies as should be. Atom with energy 2J cos K is going to couple to an atom in the excited state with 2J cos K plus phi. Exactly, it's a relabeling of everything. But in this picture, it's more simple because everything is going to be diagonal in momentum. Basically, I'm going to connect an atom with momentum Q in the ground state with the label of momentum Q in the excited state. Yes? So this allows me to write a Hamiltonian for a single particle in the presence of a spin-orbit coupling and in the presence of a drive as a spin model. We love spin models. So you can see that now there is an effective magnetic field that has two components. Well, the one from the laser that drives the ground to the excited state. And then there is going to be a detuning that besides the detuning that I have from the laser, I'm going to have an effective detuning because I reshuffle the dispersion, and it's going to be an energy difference between the excited state and the ground state in a way that depends on the momentum. So this is going to be larger here at Q equal to 0 and so forth. Does that make sense? Yes, or I'm started to lose people. It doesn't at the moment, but it's going to be, it's not exactly the one, it's not going to be the right, but it's a coupling between the spin and momentum. Basically, okay, so if you are going to have this coupling that drives, you are going to have something that drives the ground to the excited state, and you diagonalize these new bands, this Hamiltonian that has a momentum dependence, then you are going to go from these bands to some type of bands, and the composition of these different bands that are these spin orbit coupled bands are going to have a dispersion, a component in the ground and the excited state that depends on the internal level. And therefore, if you look at, basically the interesting part is that the eigenstates of the different atoms are going to be because the drive is along the x direction, is going to be some vectors that depending of the Q is going to be in the CX plane. And depending of the momentum, I'm going to have some eigenstate that lies in this plane. And then there is going to be not what is called, people call some chirality, but actually depending on where the composition of ground and excited state, where you are depends on the momentum, and that means that if you're going to do some type of transport experiment, it's going to be some preference to go in one direction compared to the other. So this is kind of at the heart of that. But let's try to look at what happens and how this modify, or how we can see this spin coupling in the clock first, and how it's going to be affect the clock operation. So in the experiment, you can change the detuning. So for a we are going to change the global separation of the two bands. So what we can do is that we can start, for example, with, we start with all atoms in the ground state. And then for this specific detuning, what we do is we are going to use a very, very weak laser that we are only couple the states that are close to resonance. Every state that is far from resonance is not going to be transferred. So by doing that, I'm able to only transfer some type of atoms, the atoms of atoms that are in a window of momentum. So this is a technique that in the clock we can use to select that specific window of momentum. We can do that for other type of the tunings, and then we are going, depends on the tuning that I choose, I'm going to choose different type of initial momentum that I prepare my atoms. And then after I have the atoms in the excited state, when I have my atoms in the excited state, I'm going to let them evolve for a given value of the rabbit drive and see depreciation in the presence of the drive. And what is going to happen is that because we are going to have, depending on the momentum that I had, are going to have different axis of orientation of the vector I will rotate around, then I'm going to see different type of oscillations that exactly what we see in the clock. For the different momentum that I choose, the axis of rotation, because of the spin-orbit coupling, is going to be different. And in fact, you are going to see that different precession rates on the clock, on the rate of the clock. And this is the theory, this is the experiment. So basically, what we confirm is that it's a coupling between the spin and the motion that is going to be directly manifested in the clock. So we see the presence of a spin-orbit coupling in the clock. And I mean, the question is, how bad is this going to be for the physics that we want to explore? Is this spin-orbit coupling okay, or what happens if we are going to operate the clock in the presence of that? So the answer, of course, is going to be that is going to be really bad for the clock. And the next set of experiments are going to be try to correct it. So basically, June had the motivation, maybe if we let the atoms evolve in the presence of tunneling, we are going to reduce the lattice depth. And if we reduce the lattice depth, scattering from the photons that create the lattice are going to prolong the lifetime of my atoms. Because when I have the atoms trapped in a lattice, then they're going to absorb photons from the lasers that create the lattice, go into an excited state and decay. That's not good. So for June, was much better to reduce the lattice depth and let the atoms move. But let's see what we saw in the presence of a spin-orbit coupling when we let the atoms move. So I'm going to do the same RAPSI spectroscopy that we did before, but now with a much shallower lattice. Before, the lattice was completely deep. Now we're going to let the same experiment, but let the atoms move. So in this case, let's ignore interactions. So in purpose, they make the system super dilute. They reduce the number of particles significantly. And the single particle Hamiltonian was going to be that different atoms populating different spins initially, because they are fermions, so you are populating different spin states in the lattice, I mean different momentum states, not different spin states, different, I mean they are going to have different spin-orbit coupling or different magnetic fields, how they evolve during the time that the laser is off. So, and what again they are going to measure is I mean, before the second pi half pulse, they want to measure the contrast, that is the length of the block vector in the plane, that is going to have a modification of the frequency and the length. So this is the Ramsey spectroscopy that I mentioned before. Now, this is what happened. Instead of having a very long lifetime, you can see that this is the lattice depth when the particles could not tunnel. There is a little bit of a decay. Now I start to let the atoms tunnel, and you see that the contrast of the Ramsey fringe decays super fast, super fast. And the model is very simple, because you can see that this effective magnetic field depends on the momentum. Yes, depends on the difference in this. There is a dependence on the momentum that is in the form of a sinusoidal function, and therefore, when you look at the evolution of all the particles, there is going to translate in the presence of a Bessel function, and the Bessel function is going to, this decay is that the contrast is going to be decay as a Bessel function with argument that depends on the tunneling. So the larger the tunneling, the larger the argument in the Bessel function, the particles are going to decay. So you can see that it's phi is the spin-orbit coupling angle. If you are having phi equal to 0, well, no decay. But because phi is not 0, that is what makes the argument of the Bessel function non-zero. And basically, if you look at, you try to look in terms of density of states, if you go back to this case, so basically, you are going to look at the points, you are going to populate all the bands, and what we care is where there is the density of states larger. And in a sinusoidal potential, the density of a state is larger in 2 points. And therefore, basically, to try to understand this decay, you can understand as 2 large spins, but now 2 spins precessing at a different rate. So I prepare the first spin, I create a pi half pulse, the 2 spins are aligned, and then each spin are going to you precede at a different rate because of the spin-orbit coupling. They are going to dephase, and this is exactly what is happening. That is going to dephase when they're going to be completely perpendicular, there is no contrast, everything is bad, and then you dephase again. So we were able to measure all of this in the clock, and this tells us that spin-orbit coupling was bad even at the single particle level. Now, what happens with the interactions? And with interaction, it was a disaster. It's a disaster because as before, we are going to have, remember that I was telling you, we are dealing with the spin polarized atoms, that they only have p wave interactions. And that's what we computed. What is the density shift in the presence of p wave interactions? Now, we are going to have atoms that are distinguishable because the behavior of an atom in one pancake is going to be different to atom in the other pancake. And when an atom is going to tunnel from one pancake to the other, is going to see the other atom that is doing something very different and therefore is distinguishable, you are going to now be subject to very strong S-wave interactions. And then it's going to be super bad. Now we're going to have terrible shifts. So what was the salvation? Now I'm going to tell you a story about clocks oriented vertically. So instead of letting the atoms move and delocalize, what we are trying to do is to prevent the motion of the particles by causing them problem to move by making my clock vertically and using gravity to actually, in our favor, to allow us to do that. Okay, so now we are going to go to the new generation of clocks that we call it the Warner-Stark 1D lattice clock. This clock is vertical, and therefore the ground and the excited states are going to now have an energy cost MGA from one particle to move from one lattice side to the other. So if you try to diagonalize a particle in a lattice with a tilt, the eigenstates are called Warner-Stark states. These states are very nice because these states can be written in terms of Warner orbitals. Warner orbitals are the eigenstates of particles at the different lattice sides. But instead of being an equal superposition, all of them, that is what happens when you don't have a tilt, the weight on the different superpositions is going to be set by a Bessel function. So pictorially, if you have the eigenstates of a lattice side at 3 recoil lattice that is very shallow, instead of being fully delocalized as you expect, you can see it still has a lot of localization. And of course, as you start to increase the lattice, it's even better. You have much more localized particles. Now, why the optical lattice clock in the tilt lattice is much better? There are various opportunities. Well, the clock was able to push the coherence time to half a minute. How they did that? Many reasons. So let's see. Particles are in a weaker lattice. So maybe you can tell me a little bit what advantage could have for a weaker lattice? If you were a clockmaker, what could be advantage? Exactly. Tunneling is suppressed. The particles are going to be not localized. I mean, so because of the till, I can operate at very shallow lattice and still not have too much tunneling. But because the lattice is weaker compared to the prior experiment, then I am going to suppress the light scattering from the laser beams. But furthermore, if I'm going to look at each lattice site, now inside each pancake, because the lattice is weaker, then the system is less dense. Yes, before the volume is very narrow and therefore the collisions are super strong. If I relax my trapping, inside the same trap, the same lattice site, the collisions are going to be reduced. And in fact, bad collisions that happen because we're inelastic between atoms in the excited states are going to be reduced. So this is one of the things that we're able to do that. So no bad P-wave elastic interactions, light scattering is suppressed, and no motional decoherence. But moreover, what we are going to do is that we were able to explore new type of many-body physics, taking into account the interplay between spin-orbit coupling, tunneling, and interactions in the system. And we are going to predict that the clock needs to operate at a specific lattice depth to suppress completely density shift, now in this case. What was the trick? So I'm going to repeat the same exercise that we did when we were having particles in an harmonic oscillator. Remember, we were saying particles are going to occupy these different harmonic oscillator levels, yes? But now instead of harmonic oscillator levels, we are going to occupy the eigenstates of the tilt lattice plus lattice plus tilt potential. That is, we are going to occupy Warnier-Stark states. This is going to be our lattice sites. Atoms are going to be in the Warnier-Stark states. So the idea, remember our Hamiltonian, and this is what is so important. Before, we have the tuning, we have the Rabi frequency, and remember that before, when we were having, we were modeling the particles in a given pancake, we were calling an effective CSC interaction. This is the same, M is the pancake, that we were saying, well, we have a collective, because it was independent of temperature, we have this chi, and we model that. So we have this term. But now, and these two terms, remember that we use for canceling the density shift. Now there is another term that appears because there is going to be a little bit of S-wave interactions. What happens is that we are going to have a little bit of the localization between particle in this pancake and in this other pancake. So because the particles are delocalized, there is going to be a little bit of matrix element between atoms in two different pancakes that are distinguishable because of a spin-orbit coupling. So that means that we have these parameters that are P-wave. They are created in the same pancake, so that's what I put a large overlap. This eta 0 is a large overlap in the same pancake. On the other hand, if I have S-wave interactions between the atoms in two different pancakes, the overlap is tiny. That's why I put an overlap here that is tiny. S-wave interactions are huge. That's what I'm going to have this. Nothing will happen if I have no spin-orbit coupling. If phi is 0, this is going to cancel. So there is going to be kind of a balancing between this term of large overlap, a small interaction, to a small overlap, large interactions. And what happens is when I write my mean field model, I'm going to do it again here, I'm going to write the mean field model. What happens is that I'm going to have an additional term here that I'm going from the S-wave interactions that I can compensate, and I can make all this term 0 for all the conditions that I want. So the idea is that by operating at the point where this term is 0, I can fully cancel the density shifts. And this happens, our theory prediction happened that the different ticking in the clock versus lattice depth can happen at a specific value of the lattice depth that we call the magic lattice. So we told June, okay, you operate with shallow lattice. Instead of going to 30 recoil, you go to 10 recoil. And by operating at 10 recoil, you're going to see that you don't have any density shift. And in fact, that's what they saw. They saw no density shift at this point. This is the experimental data. So they saw a cancellation of the density shift over 10 hours at the 10 to the minus 21. So very little, almost no density shift. And with that, and the additional 37 seconds coherence time, then it opened to very exciting development. At this condition, and for this very long interrogation time, the experiment was able to see for the first time the Einstein gravitational redshift in this system at 1 millimeter distance. So let me elaborate on that. So for GR, who are the experts in GR here? I was not an expert in GR. So, but I want to tell you something that changed and make GR much more simpler for me. That's the idea that in order to understand GR on conditions that are not black holes, in very simple conditions close to Earth or close to flat space, the only thing that you need to know is that atoms in an excited state has different mass. That's it. So if you go to Einstein formula of the mass energy equivalence, you know that E is equal to mc squared. Yes? So what happens that if I have an atom in the ground state, and this is 0, so let me put here, E ground is I'm going to set to 0 mgc squared. The important part is that E excited, in the excited state, is going to be me c squared plus h bar omega. Yes? So that means what happens is that there is a different mass between the ground and the excited state, just because the particles in the excited state has an energy difference that is of the orders of terahertz. Yes, that's the key part. So there is going to be here is going to be mgc squared. So the difference, there is a difference in mass, delta m times c squared is going to be rh omega divided by, so there is a different mass that is going to be h bar omega divided by c squared. Okay, so if we have now particles in a tilted potential, what happens? If I have particles in a tilted potential and my Hamiltonian is mgh, then because the particles in the ground and in the excited state have different mass, you have an effective Hamiltonian that is proportional to delta m, an additional term, gh sigma c, because the atoms in the ground and the excited state have different mass. Yes, this sigma c means that it's different between the ground and excited state. Yes, and therefore there is going to be a different ticking of the clock, and this different ticking of the clock, delta nu, is going to be proportional to delta m gh, and delta m is going to be just h bar omega, or delta m h bar omega c squared, and this is delta omega. Yes, for having the units delta omega divided by. That means that if I cancel this, then we are going to have delta omega or delta nu divided by nu is going to be omega sorry, this is delta M G H, yes? So this is going to be G H divided by C squared. This formula is the redshift. This is what Einstein says that clocks at different rates, at different heights, are going to tick different. So what happens is that you have a clock that is in the mountain is going to tick very different than a clock that is close to Earth. This is associated also with what we see about twins in going to different parts in accelerated frames are going to have different clocks. All of this you can get by this very simplified treatment. And that's what we measure in the clock. We are going to see that for Earth, G 9.8 meters per centimeter square, and if H is equal to 1 millimeter, this delta nu divided by nu is the order of 10 to the minus 19. And this is exactly the precision that we reached when we were able to cancel all these shifts and we were able to prolong the coherence time of the clock. So we are not the only ones. Of course, there were beautiful experiments at Nice where they have clocks separated by 30 centimeters, and they were able to measure the density shift. But we are trying to see here what happens at 1 millimeter. And what is the beauty? Well, we are not going to explore quantum gravity, but what we are trying to start exploring is what is the interplay between quantum mechanics and GR. This is different than quantum gravity. But we are going to start seeing, for example, if because gravity and you have an entangled state, is going to be some decoherence. That for sure we expect it will, yes? But this is the type of physics that we are now entering to explore in the clock. The interplay between redshift redshift, quantum mechanics, and many-body physics. So this is the experiment that was done. So the experiment over about 10 days or more, they look at what is the different ticking between the upper part of the clock and the lower part of the clock. And they compare the two ticking rates over days and measure. And what they find is that at the 10 to the minus 19, in fact, there was an overall shift consistent with that. So with that, we were able to report the first measurement of the redshift in a millimeter scale sample. Open a path for various different directions. So I think I have 4 more minutes, yes? So maybe I stop here, and tomorrow we are going to go from 1D lattice, that has been the topic of all these lectures, to 3D. And we're going to try to explore the interplay between tunneling, now contact interactions in a hover model with a spin orbit coupling, and see what is the different consequence in the system. So maybe any questions so far? Yes, so there are proposals to detect gravitational waves with clocks. For that, the clocks have to be in space, separated very far distance. But the idea is that when a gravitational wave passes, then the ticking of the clock is going to change. So basically, if you have a clock where that is in a region where the gravitational wave passes, and the other clock that is not, then you compare the frequency of the clocks, and then you might able to see the gravitational waves at frequencies that at the moment LIGO has hard time to resolve. So there has been papers on that. From LIGO, it's going to be, well, LIGO is amazing, but it's going to be in a regime, in different regime, the gravitational wave has a specific frequency, so it's going to be in the low frequency range of the gravitational waves. So different to what LIGO can detect, and I think different from what LISA is expected to detect. So the dynamical range is going to be important because it's going to determine what is the frequency of the waves that we detect. And they're going to be very low frequency. But maybe, you have to put the clocks in space, synchronize the clocks. Well, at some point, because now we see redshifts. When you report the ticking of a clock, you don't need to report only the frequency, but you have to reply the frequency and at what particular part of Earth, because it's going to change whatever, and a particular, it's going to be complicated. As the clocks get more precise, it's going to be super hard to compare. But June is having a laser, a fiber that goes and connects to a clock at NIS, and that's how they are doing comparisons between the two clocks, and there are people that are trying to do geodesic, because now that we can sense different heights, then you are going to report what is the variation of gravity across different parts of Earth. So it can be exciting. One of the selling points that we had at some point is that you can detect oil, because depending on the oil composition below, your clock is going to tick at a different rate. So, or seismic movement of, in principle, if there's seismic motion, then you can detect.
So, the LIGO has a 4 kilometer of array. The length, and the range is approx 10 to the power minus 19 to 22 or something.
Yes, it's
So
in that range.
yeah, so that small amount is possible.
In the clock, that's what we will need to detect gravitational waves. At the moment, no. At the moment, we are 10 to the minus 19, and I mentioned at the beginning. So not at the moment, but we hope we will.
Okay. And LIGO is already in the ground, so is it really necessary in space?
Well, I think it opens up, for clocks in space, the reason is that they have to be separated many, many kilometers apart.
Okay.
And that's the way that we imagine, that you put a clock in a satellite and the other in another satellite very far away, and you somehow synchronize these clocks with light, because of course they have to tick, you have to synchronize the frequency, and then we compare the ticking of this clock with the other clock. It is a speculation. It's nothing. It's a paper, a theory paper, but who knows? As I showed you the exponential improvement of the clock, hopefully it keeps going.
Can you hear me? There is a nice paper from Edwin Pedroso at MIT where they use entanglement to improve these clocks. Is it possible to...
No, be careful. They have not improved a clock. You have to be very careful.
The limits.
No, they have not. That's the problem of this paper. They have not done a clock operation and an entangled clock. The paper is misleading. And they have done very beautiful experiments, but not a clock. What they have done is entangle the nuclear spin states in ytterbium, and they are then trying to excite the atoms from the ground to the excited state and show that they can preserve the squeezing. But they have not shown a clock frequency, a clock operation that has demonstrated that the entanglement gives a better signal. Not yet.
It is misleading. Okay.
Yeah, sorry. I'm sorry to be, but that's the problem with those papers, that they're beautiful, but they're not doing a clock. They are not. No. There are papers. June is trying to do a squeezing in a cavity. This is one of the first experiments. This year, they reported 10 to the minus 18 sensitivity in a cavity. So better, but never at this level. But, that's the future, yes? I'm going to tell you a little bit about the squeezing, something that we are trying to do tomorrow, if there is time.
Okay, guys. I think we can thank Ana Maria again. go to lunch.
Yes, yes.
So just for curiosity, you people like did the back of envelope calculation, which precision would you need to detect quantum gravity?